Yeah, hang on to that paper because we still got to do the other side, but we'll save that for another day. Rest of today, I'm going to take you guys through nuclear energy. Oops. Here we go. All right, so the picture you're looking at right there is an atomic weapons test back in 1946 up the coast of Bikini Atoll. This was a plutonium bomb, which is a type of fission bomb, but let's jump into this. So I think a good starting place for the story maybe is the discovery of the neutron by these guys about 100 years ago. They realized that the neutron was a thing. So there's a nucleon that's not a proton, got a neutron. You guys remember isotopes in chemistry? So one element might have different isotopes because it has different numbers of neutrons, and each isotope might have slightly different chemical properties. So the neutron itself is composed of two down quarks and an up quark. So protons and neutrons actually are not fundamental particles themselves. They're composed of quarks, just like that. Fast forward a little bit, and you got this German scientist and this Austrian scientist, Lisa Meitner and Otto Hahn, who realized that, oh, you could take this newly discovered at the time neutron and bombard a uranium-235 atom, and that will split the atom and create new types of atoms. So they conducted the first nuclear reaction ever in history. Now, you guys remember that entire class you took called chemistry? So all those chemical reactions, which this right here is not, this is not a chemical reaction, this is a nuclear reaction, right? So chemical reactions, conservation of mass applies. So if you look at the mass of all the reactants and the mass of all the products, they have to equate. But that's not true for nuclear reactions. Now, the missing mass for a nuclear reaction doesn't disappear. It converts into energy by E equals mc squared. You might remember that from a few weeks back. Oh, there we go. E equals mc squared. So E is energy, m is mass. So if there's some mass difference due to some nuclear reaction, then that mass converts into energy multiplied by the speed of light squared. So these two graphs side by side, mass per nucleon or binding energy per nucleon, they're the same idea, just one is the upside down of the other, sort of. Right, so let me do mass per nucleon, because why not? Just pick one, right? Oh, if I said, you guys know nucleon is either a proton or a neutron, right? Protons and neutrons, which have about the same mass. But when I say the same mass, what is the mass? What is the mass of a proton or a neutron? Well, it actually depends what atom you're in. So it's really heavy if you're in hydrogen, and then it's a lot lighter if you're in helium. It looks like it goes down until you get to about iron, and then after iron, it goes up, the mass per nucleon. Or if you look at binding energy per nucleon, it's just like the inverse. The binding energy increases until you get to iron, and then it decreases for the heavier elements after that. Well, if you could have some kind of nuclear reaction, which means you're changing the nucleus from one atom to a different type of atom, well, there's going to be some associated mass and also energy change by E equals mc squared. So if you have heavy elements and you split those into lighter elements, go from right to left until you get to iron, that's called fission. And if you take lighter elements like hydrogen and you fuse those together into heavier elements like helium, that's called fusion. And either of those processes can get you energy. But if you start from iron, then, well, you're out of luck, because iron, you can never get any energy out of that by a nuclear process. Right, so here's a Chicago Pile. The world's first nuclear reactor was built in secrecy, University of Chicago, 1942, as part of the Manhattan Project being funded by the federal government. Scientists knew that in principle you could create atomic weapons, these nuclear weapons, but how exactly could you engineer these things? Well, that's what the Manhattan Project was. We were trying to beat the Axis powers to getting an atomic bomb. We didn't want the Germans to discover it first. That would have been bad. So let's look at this roadmap for the rest of the story. I told you guys there's fission versus fusion nuclear reactions, right? Fission is breaking apart heavy elements. Fusion is fusing together light elements to get energy out of either of those processes. You can also have an uncontrolled versus a controlled reaction. Now, uncontrolled is an uncontrolled chain reaction where you run this reaction and just releases neutrons that in a chain reaction release a bunch of energy from a mass of reactant all at once. Right? let's just say a bomb, right? So if you want to create a nuclear bomb, you're talking about an uncontrolled reaction. And the first one of these was at Trinity Site in 1945. Let's take a look at uranium. Now, if you pull uranium out of the ground, most uranium is actually an isotope called U-238, but that's not the interesting one that's very useful in nuclear reactions. The useful isotope for reactions is U-235. That's the unstable one, but that's only less than 1% naturally. So to be able to use uranium in any kind of nuclear process, you have to enrich it. That's to say you have to up the percentage of U-235. Now there's different ways to do that. One way that you can do this is to vaporize the uranium, put it in a centrifuge, spin it, go bzzz, and then all the heavy stuff, the 238 goes to the outside, and all the light stuff, 235 goes to the inside, and the U-235 is the part that you want to use. Now, if you can up that percentage to about 3 or 4% U-235, that's called low enriched uranium or reactor grade. So that's what's used in nuclear power plants. If you up that percentage more to about 20%, there are some medical uses. And if you can up that to 90% or more U-235, then you get weapons grade uranium that you can actually turn into a bomb. Here's what U-235 looks like that this guy's holding right here. Now, once you have that U-235, actually it is not very difficult to create a bomb at that point. All you have to, here's how you create a nuclear bomb. If you fire this U-235 at mass U-235 at a critical speed, then it will set off that chain reaction and create a nuclear explosion. Right, so there are different kinds of fission bombs you can create. So the one we dropped on Hiroshima back at 1945 was actually an experimental bomb. It was actually the first of its kind. So that was a uranium bomb. The one we dropped on Nagasaki a few weeks later was actually a plutonium bomb, which we had tested over in New Mexico in Trinity Site. Now, plutonium is actually element number 94 on the periodic table. Plutonium is actually not anywhere in the natural environment, anywhere in our solar system. So there was some event that happened 4.5 billion years ago, probably some nova explosion that created all the elements in our solar system. And the elements only go up to element number 92, which is uranium. Now, there are still elements after that, like 94, like plutonium, but plutonium is completely artificial. Maybe not in other solar systems. It might be out there somewhere, just not in our solar system. Okay, I had some videos for you guys. These are not playing, so you're missing something. I forget what, but let's just move on to their story. So, can you control this reaction? Oh yeah, I know there's a couple of guys have to take off. So if you have to take off, some of you guys showed me your pass. Go ahead, you have to. Okay. Scientists finally controlled the fission reaction in the 1950s. I think 1951 is the earliest example I can see, but and that's, if you can control the reaction, then you can get the energy at a controlled rate, which means you can create a nuclear power plant. So, what kinds of nuclear power plants can you create there? There's actually different reactor types that you can engineer. Here's a list of them, and you guys see the most popular one is called pressurized water reactor. Let's look at what that looks like. The main part of this is the Rankine cycle, that thermodynamic process that I mentioned at the tail end of a couple days back. Okay. So if you can boil water to turn a turbine, and then that will turn a generator, which will push magnets past wires, then that will induce a voltage. I'm talking about running wires past magnets. That will induce a voltage, which generates a current. And that's how most electricity is generated on the power grid. Okay. Now here you're looking at a pressurized water reactor. So going back to, you guys see these control rods here. There's a nuclear reaction happening, and this is a pressurized part of the system. And that's running through the water that's being boiled, it's that bubble. So that's not the only design, but that's the most popular nuclear reaction design. Okay. Now, okay, here's one interesting tidbit part of this process. It's something called heavy water. So heavy water involves isotopes of hydrogen that are deuterium or tritium, which means they have extra neutrons, which makes the water extra heavy, gives it interesting chemical properties, and is one possible neutron moderator to slow down the neutrons to make this a controlled process. But you don't have to use heavy water necessarily. Let me go back a couple slides. You guys see this purple one says LWGR. The LW stands for light water. So you can create a light water reactor. But if some of these other ones involve heavy water, which is like an extra part of this process. Right, here we're looking at percent of electricity on the grid that is nuclear by country. So here's us right here, United States, 20%. We get 20% of our energy from nuclear. So 20% of the energy that's lighting that screen right there comes from nuclear. 20% of the energy that's making this room air conditioned right now comes from nuclear. Right? If you go to the top of this chart, France famously gets the vast majority of its energy from nuclear. And if you go to the bottom of this chart, there are interestingly 3 nuclear powers that use nuclear hardly at all in their electric grid: India, Pakistan, and China. So there are only a handful of countries, I want to say like 8 countries in the world that have nuclear weapons. Those are 3 of them down at the bottom. So India, Pakistan, and China have nuclear technology, but they hardly ever use it at all for their own electricity consumption. Okay. Here's nuclear power plants over time. So 50s, 60s, 70s, a bunch of plants were being built. But then in the 1980s, put on pause, and hardly any plants have been built since the 1980s. Because nuclear power has huge upsides in that nuclear power is clean in the sense that it doesn't release any greenhouse gases into the atmosphere and doesn't affect the environment terribly, except of course if you're near the nuclear, the radioactive waste. So there are some downsides, of course, to nuclear power also. What do you do with the waste? How do you store the waste for tens of thousands of years and communicate to future generations that there's nuclear waste here and don't get near this, it's dangerous. And also every rare once in a while, there is a meltdown, especially like these old plants like Chernobyl. There's this meltdown. So what nuclear wasteland now, don't want to go near there. 3 Mile Island was almost a meltdown. Fukushima is not on this this graph, but be there too, right? There are actually alternate nuclear power designs that you can create, and this is one of them that are much safer, that have passive safety. So this is what you're looking at here is called a molten salt reactor. So most of the power plants in the world right now, if all the nuclear engineers running them just walked away, or they were like killed off by some crazy pandemic or something, then that would be bad in the sense that those power plants would undergo meltdowns, that there would be a runaway nuclear reactions, and that nuclear fuel would literally melt down into the ground beneath it and into the water supply, and that would be bad, right? But what you're looking at right now, that would not happen. Do you guys see this right here, this freeze plug? So if something went awry and something went wrong and not like it was supposed to, then what would happen here is that that nuclear fuel would melt this freeze plug, and then all that fuel would be dumped into these emergency dump tanks, and then the process would stop, the whole nuclear reaction. So this right here is a much safer design. Okay, so skip some slides there. The graphics for. There is actually fuel you can use that's not uranium to run nuclear reactions, like thorium. And there are proponents of thorium to use thorium instead of uranium for nuclear reactions. And here are some of the supposed advantages of thorium. One is that thorium is much more abundant than uranium, so the fuel would last much longer. We have a lot more of it. Also, the nuclear waste that comes out of it, there's a lot less nuclear waste, less than 1% of the nuclear waste compared to uranium. And also the nuclear waste that you do get has a half-life, because of the particular products from that, of only a few hundred years compared to tens of thousands of years what it is for uranium. So so it's not as dangerous for as long. Also, if you use one of those molten salt reactors, this is a liquid fluoride, I want to say, thorium reactor, it has passive safety. It has that like this freeze plug right here. So if you have one of these molten salt reactors, it can't melt down. So why are we not using thorium instead of uranium? Well, if you look at this technology being developed many decades ago during the Cold War, the thought was, well, this is one of the thoughts. It's like, well, if we have this body of knowledge of how to run these nuclear reactions, then we want both uranium plants, but also nuclear weapons. But since thorium is not useful for creating nuclear weapons, you need a whole bunch of new textbooks and a whole bunch of scientists that did not have crossover knowledge of weapons technology. Okay, so everything you guys have seen so far is fission. I know we got a couple minutes left. Let's do fusion. Now, fusion is going from hydrogen to helium, basically. Let's call it that. But you guys see how there's basically 1,000 times more energy that you can get out of fusion compared to fission. That's what it is. So 1950s, we were able to create the first nuclear bombs. The energy from the sun is fusion. It's hydrogen fusing into helium. That's the energy of the sun. Here's what that fusion reaction looks like. Here's how you create a thermonuclear bomb. Thermonuclear bomb, hydrogen bomb actually has a fission bomb built into it that kickstarts the fusion reaction. Okay. And can you control a fusion reaction and create fusion power plants? Well, probably, but we haven't yet. So here's Lawrence Livermore Laboratory outside San Francisco where they're trying this. Here's a more recent picture of a fusion reactor. Now we have been able to create fusion reactions. The catch is that there's been more energy input than output, so it's not economical yet. I heard a recent Department of Secretary of Energy say that we're probably about 10 years away from developing fusion power at this point. Here's a recent science article. There actually was a recent breakthrough in fusion technology. So we're not quite there yet, but we're getting closer. And once we develop fusion power plants, then we are good to go in terms of energy. So anywhere about fossil fuels or wind turbines or solar is all out the window because basically all you need is seawater, which has lots of tritium and deuterium in it as your nuclear fuel. And we have so much of this, it's so abundant that this will be the dominant component of our energy mix. All right, just in time. So hope you guys enjoyed the presentation on nuclear energy. You guys have a good rest of your day.